Hello everyone. For this tutorial video, I'd like to explain how to analyze series parallel AC circuits, which will actually be very similar to DC series parallel circuits as if the components were just resistors, as we should already be able to predict at this point, because of how we saw that was true for series and parallel circuits individually. If we were given an example circuit like this, we would first calculate the reactances of all the capacitors and inductors individually, using the formulas we derived earlier. Then we would convert them into polar form to express them as impedances we can add. But then we would notice that they do not follow a simple formula as if it was series or parallel alone, because of how complex the circuit is. But what we can do is condense parallel branches as appropriate into an equivalent resistance that is part of a series. So what we would do in this case, as we have one parallel branch in the circuit, is to combine the capacitor and inductor in one branch as a series. So we would add them, but pay attention to the fact they have different phases. And then we would calculate the total impedance of that in parallel to the resistance given, using the parallel resistance/impedance formula. Then finally, after we calculate that impedance, we would add it in series with the impedance of the last component, which was the first capacitor, and conclude that is the total impedance of the circuit in general. The voltage and current will be equally as problematic in the circuit, so we would use the same thought process, namely, we would see because it is the first element in a series, the current across the first capacitor must be exactly equal to the current of the source, which we can figure out as the voltage given divided by the total impedance we calculated earlier. Then we would see for the parallel branch after the first capacitor, the total current must be equal to the current of the capacitor and source, but the current across each part of the branch would be different. And the same problem comes up for the voltage, but what we can do is state the voltage across the first capacitor equals the current we found times the reactance of that specific capacitor. So next, we can state the current across the inductor and capacitor in the parallel branch is exactly equal, although we do not know what the exact value of the current is yet. But what we can state is that the total voltage of that branch is exactly equal to the voltage of the resistor parallel to it by parallel circuit rules. So since we know in a series circuit the voltages must add up mathematically to get the total voltage, we can correctly guess that the voltage across the resistor in the parallel branch must be the voltage of the source given minus the voltage of the first capacitor calculated earlier. Although obviously the problem with phases would come up with that calculation again. It would not be a simple arithmetic subtraction. And since we know in a parallel circuit the currents add up, we should be able to guess that the current in the more complicated branch is simply the total current we found from the first capacitor earlier minus the current of the resistor. And it will be the same current hypothetically across both the inductor and capacitor by the laws of series circuits. So now that we know what the current and reactance is for the individual components, we can lastly compute the voltage directly using Ohm's law. Before I move on to discussing specific types of RLC circuits, there's one last detail I'd like to note that is also similar to DC circuits studied earlier. Namely that for a parallel circuit, whether a simple one or a parallel junction like in this video, there is an equivalent to conductance for reactance called susceptance, and there is an equivalent to conductance for total impedance called admittance. So you can express parallel circuit formulas with susceptance and admittance if you want, although the numbers will still be the same, because of the fact you have to convert back to the inverses before you get your final answer, which was the same problem encountered when using conductance to simplify resistance calculations. Now that I have thoroughly explained how to solve complicated circuits that involve all three components at the same time, I can explain useful applications of this type of circuit in my next tutorial videos, starting with an explanation of what a tank circuit is and what resonance means in electronic engineering. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.